So now we directly move to the last session of this meeting. We have two talks by the two editor-in-chiefs of IJMF Journal. We begin with Professor Soldati. Professor Soldati is the head of the Institute of Fluid Mechanics and Heat Transfer at TU Wien. He is the editor-in-chief of International Journal of Multiphase Flow and serves as a member of the editorial advisory board of Physics of Fluids. His research focuses on turbulent multiphase flow with environmental and industrial application. So, Professor Soldati, the stage is yours. You can get started when you're ready.
So thank you very much. I'd like to thank you and Professor Pakanjula for inviting me to this meeting. And I will start immediately presenting my talk. And in my talk, you see the topic I would like to cover. And you see it on the bottom. And the nice picture you see is not really a real picture, but it's just a result of a simulation, which to me seems really real. So it's something that I like a lot, and it was made by, in particular, by Alessio Rocconi. Now, before I go into the technical details of the presentation, you mentioned that, and the IJMF was mentioned already, and I am now into this, sorry, just 1 second. Okay, into this adventure of the, into this adventure of international multiphase flow. I know Bala since 2004. He organized a very nice meeting with Andrea Prosperetti in Chicago, in Argonne. And while everybody was going to the concert, Bala, I, and other two colleagues became the bad boys, and we didn't go to the concert, and we actually went to a nice dinner and had very nice, good drinks. So I know Bala since many years, but I really started to know him much better with this new big adventure as a co-editor-in-chief of International Journal on Multiphase Flow. This journal was founded by Gerd Stroni, who had this vision, and eventually was led by Andrea Prosperetti just until a few years ago. And then since 4 years, it's the two of us who are running this, this journal. There is some work, it's lots of fun. We can have a very good perspective of what's going on in the entire world. I have a double work because one work is being the editor, and the other work is just to try to damp Bala because he's so volcanic and he wants to do so many things and would add more work to the lot of work we already do. So I have to somehow to stop him to include more and more activities in our journal. Just a few words on the performance of the journal. Andrea took over the journal in 2007 after Stroni, and he did a great job in increasing the impact factor and the number of publications and the number of quality publications in the journal. And we took over. We are not at the same increase that Andrea was able to do to this journal, but we are still increasing, and we are thinking that we are that the journal is doing rather well. Our impact factor is now rather high, well above 3. And the interesting thing is that although initially we increased the number of papers we publish, since a few years, the number of quality papers that we are publishing is more or less constant. So we publish more or less 250 papers per year, which is not bad for a journal like of our size. Now I go back to the to my presentation, and I will immediately speak about the motivations and issues. So let's suppose you have a turbulent jet, liquid jet that breaks, and you want to compute the drop size distribution of into this jet. So you will see that, of course, the drop change, break, collide, coalesce, and then eventually you want to know what is the drop size distribution. What instrument do you have for this? Well, for the moment, you just don't really have much. There is just some theoretical work, which is in fact based on scaling arguments. And this theoretical work is telling you that the number of drops depend the distribution of the number of drops per radius in millimeters, drops or bubbles, is the same, goes with 2 different slopes. And there is a very interesting crossover at this point. The crossover is actually called the Hinze critical radius, and it's the point at which a bubble, which is deformed by the shear in the turbulent flow, actually is restored by the surface tension. So it's the point at which bubbles don't, this point is the point at which bubbles don't break. But Can we estimate the slope of these other two curves? Yes, of course we can, but we can with scaling arguments. And it turns out that the small drops have a scaling of alpha. The exponent is alpha equal to minus 1.5, and the large bubbles, which are continuously formed and continuously coalesce and mostly break, forming the small bubbles, have an exponent which goes as minus 10 over 3. So it's more or less minus 3. There is some dispute now. So this is the most we can have now to estimate the drop size distribution. And we would like to do a little more. But the problem is that the interface of bubbles is so small. The interface actually as a scale of molecules, so it's a nanoscopic scale. And if you look at the scale which separates two bubbles or two drops when they're close one to each other and they're tending to break or coalesce, it's already very small. This size is mesoscopic. It's more or less the drop size or the bubble scale size. But if you put all these things into a real turbulent flow, like a wave or a jet or something that breaks, then you are really going to macroscopic scales of the order of the meter. Now, what you want to do? Let's suppose you want to do a simulation of everything, including the molecular scale and including the turbulence, so the macro scale to the micro scale. So you have a separation of the scale of 10 to the 9 meters. And if you want to do just a single phase turbulence, in fact, the separation of scale is 10 to the minus 3. Now, if you want to solve everything on a large computer, whatever large computer you can find on our planet can give you 3 or 4 orders of magnitude span. So your choice has to be, do I want to use these 3 or 4 orders of magnitude to simulate the small scales or the large scales? Possibly it's better to simulate the large vortices, but at this point, then you have to simulate also the small vortices and come up to a model for the thickness of the interface. And in this plane, you can see we just try to regroup all these possible models, from Lagrangian particle tracking to molecular dynamics and to interface resolved simulations. This is the characteristic drop bubble size, and these are the resolved scales of the flow and of the interface. So in this talk, I will focus on the interface resolved simulations, in which all turbulent scales are resolved, so down to the Kolmogorov scale, and we assume that the droplet size is comparable with the turbulent scales. With which method do we want to do this? Well, we have to do 2 things. We have to solve the flow field, and we have to track the interface. And for both of these 2 things, we can use a sharp approach or a continuous approach. And our solution, in fact, is described by the red line. Just to mention, among the sharp approach for the flow field solution, there is the Gauss fluid method, and among the continuous approach, there is a force coupling, so which is a method used, very famous method used by Greta Tryggvason, and the phase field model, which is the one we will use. Same for the interface tracking. Sharp approach includes the front capturing or the volume of fluid, which are mostly used. And among the continuous approach, there is the level set and the phase field model, which is based on a Cahn-Hilliard equation, which is the one we are using. I will not go into the details of the method, but I'll just show you what is the difference between a sharp interface approach and a phase field approach. A 2-dimensional drop or a 2-dimensional bubble in a sharp interface approach will have exactly a sharp interface. Here there is the drop. Immediately, 1 cell later, in the neighboring cell, there will be the carrier fluid. If you have a diffuse interface, you have a gradient in the descriptor of the phases, which can go, so phi can go to -1 to +1. And this descriptor of the phases, the concentration of this descriptor, actually has a smooth transition, in the middle of which, so at 0 of the value of this descriptor, you have, of this color function, say, you have the interface. Advantages and disadvantages of both methods are rather clear. I will not discuss them into the details. I will just tell you what do we do once we use the phase field. So we have to solve an equation for the phi, which is the scalar function. And according to this phi, proportional to this phi, we include an effect of the surface tension. So the Navier-Stokes equation will actually have an extra term, which is the coupling term, and it is the effect of the surface tension. I remind you here that if you have just the surface tension can act only in the perpendicular direction to the surface, not tangential. Two problems we have in the simulations, breakage event and coalescence events, which are the ingredients that form the population size distribution. If you have a breakage event, then what happens? A bubble stretches, and at some point you have a neck, and then at some point the neck becomes smaller than the grid size, and once it is of the order of the grid size, then the neck doesn't exist anymore. Of course, we have the problem of the grid size, but since in real physics the breakage event is very quick, we don't really have with this type of methods problems in simulating breakage events. However, when we do have a coalescence events, the coalescence is a bit more complicated because two bubbles come close to each other, and since they come close to each other, then they must squeeze out the flow in between. And to squeeze out the flow in between, it may take a little longer. You see the time units. And in this little longer, then perhaps we can have fake coalescences. So numerical coalescence or coalescence due to the method. So coalescence is a bit problematic in every method. Now, results of our simulations. I will use just a channel flow. And in this channel flow, I will throw a turbulent flow. So I will have a turbulent flow, and the Reynolds tau, the shear Reynolds number is it's a DNS for the single phase flow at the shear Reynolds number of 300. And this is the initial condition, which is immediately forgotten by the bubbles. So we can use several initial conditions. In this case, I'm showing you what happens if I put a sheet of liquid layer in between in the middle of this turbulent flow, and we will form the drops. And at some point, when we start taking statistics. Now I'll just show you what is the effect of number of drops over times. In this case, the initial condition of the bubbles was just spherical drops, which eventually will break and coalesce. You see that here I'm just showing you the effect of surface tension, which is the Weber number, which is the inverse of the surface tension. And in this case, I'm just maintaining same viscosity and same density of the two fluids, but I will just impose the effect of the surface tension. And you see that with time, the effect of the Weber number, which is going from very small, so very rigid drops, to very large, so very deformable drops, you will see that we change the regime from coalescence regime to breakup regimes. When the Weber number is very small, it's almost impossible to break the bubbles. And you can see that if the Weber number is rather high, so the surface tension is rather small at 3, we can have a plateau in which breakage and coalescence evidently balance. Balance in a dynamic balance, they are not just stopped, they coalesce and break all the times. This is just the typical simulation that we use as benchmark, but now we will go a little further up, and we want to see the effect of a different density and a different on the different density and a different viscosity. We want to change the density of the bubbles and the viscosity of the bubbles compared to that of the fluid. Density and viscosity, obviously, in this case, are proportional to the concentration of the color function phi. So they will change smoothly across the interface. And this is the Navier-Stokes equation we are solving. So we have rho, which is a function of phi, and eta, which is the viscosity, which is a function of phi. Again, we have the surface tension forces, the capillary forces, which multiply the Korteweg stresses, which is just defined here. And we are just advecting and diffusing our scalar function, which is phi. What are the simulation parameters? We change the ratio rho and the ratio eta r and rho r are the ratio of the always drop density and drop viscosity, drop properties at the numerator, and carrier flow properties at the denominator. So we change the drop, you see, from 1 to 1/1000, but we do not increase the density of the drops compared to the density of the fluid. And we change the viscosity, in fact, having drops which are either with larger viscosity in this case, or with smaller viscosity. We also do a simulation in which we combine the effect of density plus viscosity. So we change these things separately, but we can also do a combined simulation in which both viscosity and density are smaller in the drop than in the carrier fluid. So trying to simulate what happens to bubbles. So we do all the simulation for 2 Weber number, 1.5 and 3. What happens? Here in this plane, you see just pictorially what we have. In this axis, we have the density ratio, and in this axis, we have the viscosity ratio. So you see that if we, here, the viscosity of the drops is very small, and here the viscosity of the drop is very large. And you see that just going into the viscosity effect, we see that without changing the Weber number, drops seem more rigid if we increase the viscosity, which is rather natural. If we change the density, we don't see really a major effect. If we just look at the number of drops, which is the quantity which we control, we see that there is not really much different between if we change viscosity or if we change density, although the shape of the drop is very different if we change the viscosity. Mind you that we change the viscosity 4 orders of magnitude. If we change the Weber number, however, and so if we go to the breakage regime and not to the coalescence regime, we see a very important effect. If we change the density, there is not really a major difference. We see that even the shape of the drops and the topology of the flow is more or less similar. But if we change the viscosity from very small viscosity inside the drops and very large viscosity inside the drops, here we again see a change in the shape, a qualitative change in the shape of the drops. But we see also a very important effect. So if we change the viscosity, and if we increase the viscosity, and if the surface tension is not extremely strong, then we have drops which don't break anymore. So increasing the viscosity of the drops forbid breakage. But density has no effect. In fact, density has some effect. And look at here. Here we color the outside and the inside of our flow with the turbulent kinetic energy, which is this one. And you can see that if we go from very small viscosity of the drop to very high viscosity of the drop, the turbulent kinetic energy inside the drop changes a lot. Here, it's not easy to see it, but you probably can see that we have a finer turbulent structure than outside the drops. And this is obvious since we decrease the viscosity inside the drops, we are increasing the Reynolds number inside the drop. So the turbulence here has a finer scale. But if we have a very large viscosity, we are reducing the Reynolds number and the flow inside the drop seems almost linear. Same effect we have if we reduce the density, very interesting. So if you have density of the drop equal to the density of the carrier fluid, we have more or less same structure of turbulence. But if the density of the drop, which is now 1/1000, that of the carrier fluid, so we have so these are just bubbles. Inside these bubbles, we really have no turbulence. And this is because there is not enough inertia to convey and propagate the turbulence. We can also come to a nice plot in which we plotted our results. And here we have the turbulent kinetic energy as a function of the density ratio. You see the density cases here, and not the viscosity ratio. As discussed before, if we increase the viscosity inside the drop, we have a slight reduction, which is not that slight because here is a logarithmic scale. We have a reduction of almost half an order of magnitude of the turbulence kinetic energy inside the drop. But if we decrease the density inside the drop, the turbulent kinetic energy inside the drops vanishes totally. Here is 0. There is not a strong influence of the Weber number. Okay, So we just told you what happens if we change the properties inside and outside the flow. But what happens, I think I still have 5 minutes, so I will tell you what happens if we add surfactant. Now, in real life, there is not a pure fluid. All pure fluids are affected by surfactant. And this is a simulation without surfactant, and this is a simulation with surfactant. Now, in these simulations, viscosity and density are kept the same. There is just surface tension, and we add a surfactant. Surfactant here is colored in yellow and red. Yellow, high concentration of surfactant, red, low concentration of surfactant. This is the same flow, but if we add surfactant, we see that the qualitative picture of the flow is totally different. We have much more, many more small particles, and the drops seem much more deformable than before. But particularly, we see many more small particles. Intuitively, what a surfactant does, a surfactant does reduce the surface tension. So if it reduces the surface tension, then it should lead to more breakage. And this is intuitively captured by this simulation. But let's see in more detail what happens. Now, first of all, the equations. If we add a surfactant, then we have to be prepared to do something which will have to take all the non-uniform surface tension. So the surfactant, and I will come to this in the next slide, will actually produce stresses which are not only capillary stresses, so not only perpendicular, but also tangential to the surface tension. And in this way, we have to modify this function. The surfactant is a function of 2 parameters. One is beta, which is the strength of the surfactant, and the other is psi, which is the concentration of the surfactant. Of course, we have to include a further equation, a further advection diffusion equation, which transports the surfactant all along the flow field. Now, this is just what happens to the phase field and the surfactant. The red is the phase field. Here is scatter flow, -1, and inside is bubble, so +1. And at the interface, we have the surfactant. So the surfactant has these very interesting properties that we distribute it everywhere. So we distribute it inside the flow, inside the bubbles, on the surface, but it likes to stay on the bubbles. And it likes to stay on the bubbles with a layer which is one single molecule, one molecular layer. And in this way, if the surfactant if there is too much surfactant on the bubble, then it goes back to the fluid, and then it can go back to the bubble. So we simulate in a situation which can be interpreted as a real situation. So the surfactant can go everywhere, not only on the interface, and it can reach a maximum concentration of the interface, which is a function, of course, of the thickness that the surfactant layer can have. What is the important role of the surfactant? If 2 bubbles come close to, why the surfactant is able actually to induce more breakage? If the surfactant, if 2 bubbles come in close contact to each other, then there is an effect of gap draining. So the flow is actually drained because these 2 bubbles want to come closer. But if there is this gap draining, then at the same point, we have a shear in this, on these surfaces, and the shear produces an advection of the surfactant along the interface. So the surfactant from the white region goes to the black regions. And however, the surfactant does not want to be accumulated. So the surfactant tries to go back. And once the surfactant tries to go back, it actually produces a counter shear, which produces a stress, which is called Marangoni stress. And this is the Marangoni flow. This is the way in which surfactant actually do modify the behavior of the surface tension on the bubbles. The problem is that in this case very complicated, because this is the shear stress on a small drop, and you can see that the shear stress tries to advect the surfactant from certain regions to other regions, so from the red to the yellow, and then the surfactant itself tends to go back, and it produces the Marangoni stresses, which eventually act back on the flow. So the situation is very intricate. I will show you what is the number of drops over time. We just started with 256 droplets, and if the Weber number is small, so high surface tension, we see that if we increase the strength of the surfactant, then we have less coalescence and more breakage. You see the situation on a qualitative view in these pictures. But if the Weber number is already small, we have a huge increase in the number of drops, indicating that we have a huge increase in breakage events. And you can see that really the drops are much smaller. Finally, are we able to capture what has been already predicted by scaling laws? Yes, we believe we are. And we can, our simulations are all these simulations with these dots, changing effect of surfactant, changing the strength of surfactant, changing concentration of surfactant, and also changing the resolution of our simulation. So simulation at twice refined grid. Having a simulation much more refined actually can change only the amount of small bubbles, but it doesn't really change the slope of the curve for the large bubbles. So we are very happy because we are not sure from this messy graph if we are able to reproduce the scaling laws produced by other works, but definitely we don't go against it. So we are pretty happy that at least we don't deny previous works, and our work is in good agreement with that. I think I'm now almost at the end, and I would like to close, I think should be on time, and I will close with a virtual toast to Bala for his jubileum, and I really look forward to really have a toast together. Here, I can afford to have the most costly champagne in the world, and please drink a lot. Bye, Bala. Best wishes for your jubileum.
Thank you, Professor Soldati, for that impressive talk. We can take few questions.
Can I
Yes,
ask Alfredo, that picture you showed at the very first slide was stunning. It was very good. It showed a variety of scales. But one question I have is that we had earlier several talks that use AMR techniques to resolve the fine scales. I don't think you're using that, right?
No.
There are advantages and certainly disadvantages. So you want to comment on the simplicity of having a uniform or regular grid versus the necessity for AMR in this kind of problem?
Thanks, Bala. In fact, we don't really have one single grid, but we solve the problem on different grids. So we solve the problem, we solve the turbulence problem with one single grid, which is a grid refined enough to capture the order Kolmogorov time scale, length scale. And then we double the grid refinement to solve for the phi, so to reduce the thickness of the interface, and then we double again the grid to solve the advection diffusion equation for the surfactant, because for that we need a much more refined grid because we need to capture the small gradients of the surfactant. The solution is, the most important solution is the one of the Navier-Stokes equation, and the other advection diffusion equation just are not extremely costly. So this is why we can afford this. We are not using models, but we are just, of course, using computer power to to push our solution to the maximum, which is still by far not enough. Anyways.
Thank you.
Is there any other question? If not, thank you, Professor Soldati, once again for that wonderful
Thank
talk.
you.